Hi, I'm Wallace Kelly, and I had a student recently ask me some questions related to the stack, related to heap, related to reference variables, and the use of the new operator and how that all works together. So I'm going to address some of those issues now. The important things to take away from this talk are that local variables are allocated on the stack, class instances are allocated on the heap, and the reference variables and those instances, they're really distinct from each other. I'm going to show you some examples and draw you some pictures to really drive these 3 points home. So as I mentioned, memory is separated into 2 areas. There's a portion of the memory called the stack, and that's where local variables are allocated. And then there's a portion of the memory called the heap, and that's where instances of classes are allocated. All throughout this talk, I'll be using this class person. It's a simple class with a simple string name and an integer age. So if we were to declare a variable of type person, as you see here in the C# code, person P, this doesn't mean allocate enough space for a name and allocate enough space for an age. All it means is allocate enough space for a reference to a person. So person P merely declares a variable. That variable is allocated, the space to store that variable is allocated on the stack, and initially it's undefined. It has no value. It's just random bits. So if we were to write code that said p.name equal Wally, like shown here, it wouldn't compile. The compiler would say use of an unassigned local variable because it had detected that we hadn't set p equal to anything. We could get this to compile by saying p equals null. And in that case, we're zeroing out this reference. We're saying that this reference doesn't point to anything. This variable p, it doesn't point to a person, but I'm going to null it out. So this would compile, but at runtime, when I try to set p.name, the runtime will detect that the object reference is not set to an instance of an object, and it'll throw a null reference exception. Now let's compare this use of variables of type person with actually allocating a person. We allocate all the space needed for the data members of a person by calling the new operator. So here you can see I called new person, and on the heap I get enough space for a reference to a name and enough space for an age. Now, instances of classes, the member variables are a little bit different in that those are initialized. So here you can see that name is actually set to null and age is set to 0, which are the default values for reference types and integers. Of course, this program doesn't do anything useful yet, and so what we have to do is somehow store away a reference to this person out on the heap if we want to do anything with it. So in my code, I could say person P, and I could say new person, and these would be completely distinct from each other. My variable P isn't pointing at person yet, and in fact, it's not initialized. But of course, what I would most likely do is say P is equal to new person, and so now my code has a variable pointing to this memory space that has all the data associated with each person. More often than not, we'll simply write the code like this on a single line of code, person P equals new person, and this can be somewhat deceptive if we don't understand that the variables and the objects they point to are really distinct from each other. Now, once I've allocated this new person and I have a variable pointing to it, I can access the members on that person with the dot operator. So p.name means go to the person that P is pointing to, go to the name field and set it to Wally. Now I should point out that name here is a string, and string is also a reference type. So you'll recall as I back up that name was equal to null. Then when I say p.name equals Wally, what really is going on is that a new string is allocated, or rather I'm pointing name at my string that has Wally. And in fact, string is an object that contains an array of characters, and so that points to another character. But I'm not going to draw that every time. But I just want to point out that yes, name itself is a string, and so that points to other objects on the heap. Here I now set p.age equal to 40. Go to the person that the variable p is pointing to, go to the age field, and set that to 40. All right, well, let's continue on. And now what I'm going to do is modify my person class so it contains a constructor. So I have a constructor here that takes in the initial values for name and age and set those. And that's for convenience. So that now on a single line of code I can say person P, there's my variable, allocate a new person, and here are the name and the age fields because that's how I define my constructor. What if after allocating that person, assigning its location to the variable P, and then what happens if I set P equals to null? Well, the answer is that I lose that reference. These are all nulled out. The variable P is nulled out, and I lose that connection that was between my variable and the object. And so now nothing is pointing at person. Sometime in the future, the garbage collector is going to run, and this memory that was allocated for person will be freed up and made available for other instances of objects. All right, let's look at some other examples. Here, person P equals new person. Now I've allocated a second person. So I do the new person, allocating another person out here on the heap, and if I didn't assign that variable, if I didn't assign what's returned by the new operator to some variable, I would never be able to access that person again. But what if I said, now P, now my variable P, is pointing at this new person? Well, now this variable P is pointing to this instance of person, the second one, and I've lost my reference to the first one. And once again, the garbage collector will come and free that space up later. All right, let's look at some more examples. Let's suppose I allocate a second person, but this time I store away a reference to that second person. So now on the stack I have two variables, person 1 and person 2, and they're both pointing at different instances of person. No surprises there. Now let's step back and set our person class aside for a moment and think about some value types. Person's a class, it's a reference type, so it works just as I described. There are some, what you might think of as native types or primitive types, or in what we call in .NET, what we call value types. And integer is an example of that value type. And so in this case, what happens when I define or declare a variable of type integer called age? Well, local variables go on the stack. So space is reserved on the stack to store an integer. And unless I set it, it's just garbage bits, it's undefined. If I set it to something, then that value gets written right there into the stack for that integer. Now, let's suppose that I create a new person. Person P equals new person. And I have person.name, I've set it equal to Wally. And now I want to set the age. And the question is, what happens down here in the code if I say p.age equal age? Well, because integer is a value type, what happens is that value that's in the age variable, that value 42, gets copied out here onto the heap, and now the person.age has that value of 42. That value is copied. So after executing it, there is no connection any longer. Even though we say p.age equals age, there's no connection any longer between the variable, the local variable lowercase age, the integer, and the field of person age. Because that's a value type, that value is simply copied over. In fact, if I change age equal to 73, my lowercase age, that has no impact on my person. Alright, so now let's look at reference types that contain reference types. So we have class person, name and age, but now this also has another field of type person that points to a spouse. And so whenever I allocate class person, enough space is reserved not for a whole nother person, but simply for a reference to a person. You can almost think of it as a pointer. So here in our class, in our simple static void main, person P1 equals new person, person P2 equals new person. We have those two persons out there. Now what if I want to set spouse? So I want spouse here, which is currently null. I want this to point to the second person. So in my code, I would say P1.spouse equals P2. And what that would do is it would say go to the object that P1 is pointing to, go to the spouse field, and set that not to null, but set it to whatever P2 has. Well, P2 has this reference, 2, 3, 4, 5, 6, 7, right? So what would happen is the first person.spouse would have 1, 2, oops, have a little bit of a mistake there. So let's see, is that right? Yep, that's a little bit of a mistake. So let's correct that. So this should be 2, 3, 4, 5, 6, 7. Glad I caught that. Yeah, so person 1, the person that person 1 is pointing to, the spouse field is now pointing at the person that person 2 is pointing to. Now, let's think about how these references work when you're passing them to methods. So here we have a method called celebrate birthday, and it takes in a reference to a person. We're going to call that method celebrate birthday with a person P equals new person. So here, when we're at this line of code, person P equals new person, we have this familiar diagram with the stack and the heap. Then when we're about to call in to celebrate birthday, space is allocated on the stack for the local variables in that method. And that includes the variable person that gets passed in. So we have space on the stack for the variable person, and because we celebrate birthday passing in the variable P, the value that P has in it, the reference of P, gets set to the reference person. So now both the variable P and the variable person are pointing to the same instance out on the heap. Then as we advance through celebrate birthday, you can see that the code says go to person age and increment the age by 1. So that incremented the age from 40 to 41. Then when this returns, the person variable, the lowercase person variable, goes out of scope, and because it's on the stack, it can be conveniently deallocated by simply moving a stack pointer down. And so it doesn't have to be garbage collected, it merely goes out of scope. But this object out on the heap, we still have a variable pointing at it, the lowercase variable P. Let's do that similarly. Let's call a method that creates an object on the heap and then returns a reference. So here I have a method create person, and what it does is it allocates a person on a heap and then returns it. So as we go into main, space is allocated on the stack for the variable P. It's initially uninitialized, and then as we execute create person, space is allocated for our lowercase person variable. We create a new instance of person, lowercase person points to that new instance, and then we returned the value of that reference. So when this returns, the value 1, 2, 3, 4, 5, 6 will be copied into our local variable P, and because the variable person was on the stack for the create person method, it can be conveniently deallocated, and then our method can continue. And now person, this lowercase p, has a reference to the person that was allocated in this other method. Alright, so let's review what we've covered. We've seen that local variables are allocated on the stack, class instances are allocated on the heap, and reference variables and instances. It's helpful to keep in your mind that those are really distinct from each other to help you understand how those work. I hope that's been helpful. I'll see you next time.